configuration with a slower charge rate. That there's no cloud. I mean, that is technically a cloud. What are you hitting me with? Is this a joke? You ever been burned by a hardware simulator? Not burned like physically burned, but did you trust one and then after you fully invested in using it in your development pipeline, you discovered that it doesn't actually handle your hardware configuration correctly? Well, we here at Tulip Tree Technology are here for you. We've built an emulator that simulates all the aspects of a board that your firmware is going to interact with. We handle buses like I2C and SPI and timers and CPU exceptions and worry about clock domains, the whole lot. Okay. Well, we're not clock cycle accurate because that would take way too long to boot up, but we do handle a lot of the eccentricities that your hardware could throw at us. And it comes with more than just blinking LEDs and stuff, okay? We've got the same emulator you're going to see today can run Linux on MIPS 32-bit, 32 big Indian-based ADSL router. We have accurate relative timing through clock domains, so that can enforce proper initialization of peripheral devices and their clocks. And we can run actual RX vendor firmwares for a Tri-Core 375, like the firmwares themselves, not like pieces of it, the whole thing. Okay, so today we're going to be building on top of our last project. We built a board with an I2C charger, a battery, and an OLED screen that displayed the status of all those devices. And then we'll be doing some fault injection testing to make sure that our firmware handles these error conditions correctly. And we're all doing this with AI because this executive emulator is AI forward, it's AI leaning, it's AI whatever. All right. I'm Ryan Torvik with Tulip Tree Technology. I'm going to show you how to build for your board without your board. Let's go. So this is the project configuration from the STM32 CubeMX perspective, all right? Got all these things enabled. So we've got the timers we got the I2C 1 and 2, the SPI 1, 2, and the starts. We've got all these GPOs and WIDs and all that stuff. So all that's configured and set up, generated the code and put that out there. And then here's the project itself. The README here has got a decent description. I found it interesting that the README doesn't mention anything about using Emerson to do any of this and to test it in. It still talks about using flashing there, so maybe we'll have to fix that along the way. Okay, so we've got a Cortex M0 base board generated with that, built with the HAL. We've got 2 I2C buses, 2 SPIs, and all this other stuff, and it's targeting a charger application built around I2C peripheral controls. Okay, so if you remember, we've got this BQ thing, and a MAX thing, and an SSD thing over there. We got the source code from that. If we run that inside of Emerson, we'll be able to see that it's actually doing that. So let's go and do that really quickly. Do this here. Load. Page here. So, and I had listener write in. Listener? Watcher? Viewer? Colleague? Whatever. Listener wrote in. Said, hey, you just used the GUI. You didn't tell us what it does. Well, this is the emulator console that we've got. It's got a bunch of different boxes and everything too. So there are many ways of interacting with the emulated model. And this is like the most human friendly. So we've got the ability to look at serial boxes here. We can look at registers. You can look at memory. There's all sorts of different things. You can pull up any of the devices in here and look at if they've got registers. You can just look at the registers for the SSD there. So there's page 0, page 1. You can look at the hardware registers for the ones we've been interested in the most are here, even like this. And you can look at the values of those in real life, in real time, while things are going on. So you can, I like to use this just kind of verify, hey, this is what's happening so I can see it, because it's difficult to get an idea of like, oh, what's actually happening? What's going on? So we use this to kind of do that. There's a log down here. We've got a console up here that it's a device tree. It's similar to router OS. You can do an LS, you can CD to the Cortex M0. Okay, it's got devices underneath it. It's got registers underneath it. You can see registers, so you can see all the different registers that are there. So yeah, there's all sorts of things. So this is really useful for seeing how things are going. So there's the system. We hit on go here. You can see that the battery monitor is there, and we've got this and this and this. Okay, and what we're going to do today is we're gonna build off of this, and we're going to click buttons. So one of the things that you could do as a person is you can go through, let's do this here, and we'll go that way. And we can say actions. Okay, so we've got all these different actions that we can do. And we can say, let's see, what can we say? Let's say unplug. Okay, we'll say it's unplugged and see what happens. Now you'll notice the OLED didn't update. I clicked on unplug, it didn't update. Why didn't it update? That's weird. Okay, we can say done. I didn't change that either. We say fast charge, not charge, pre-charge. That's interesting. So we're interacting with this BQ device, but I'm not seeing the screen update. All right. It said the code was working just fine, but I don't know. I don't know what's going on. So what we're going to do is we're going to tell it to go through and do some of these actions and click on things with both the BQ and the other thing, the Max 17. I'm going to say, okay, interact with these actions over here. Power on reset. You know, I'm clicking them by hand, but the AI can go and run commands that will actually set these things. Okay, you set the drain rate, set the battery voltage, quick start, you know, whatever. So they got these things that you can do that, but you'll notice that it's not having the effect. Like, why isn't it having an effect on the OLED? So we're gonna let them go and do things and then see and debug it. See if is there something wrong? Am I doing everything right? Like, what am I thinking? Okay, so let's bring that up now. Boom, boom, boom. And dear listeners, I have not actually tried this out yet. We're doing this live. All right, so we have an I2C charger and battery attached to this board and an OLED display that displays the charging status, okay? Use the Emerson skill to run the simulation for this firmware, and then use device actions to manipulate the charger and battery and verify, or does it validate, that the OLED screen updates like you would expect it to, okay? Let's go, let's see this. I don't know, Luke is yelling at me right now. He's like, well, you should use spec-driven development. You should, but it's like, I get it. There's much better ways of actually doing this from an AI standpoint. But I want you to see that the AI, even without, you know, sophisticated prompting, can use this emulator and kind of go through this. I actually wanted to make mistakes. I wanted to go in the wrong direction. I wanted to find its way through. So there's more efficient, more effective ways of doing this, but I really want to demonstrate that using this, the AI can weasel its way around and actually figure things out. Okay. Session's already running. Let me check the device tree. That's true. I did leave the session running. I could have closed it. Okay. So here's the current display. Oh, it got up to 100. It got up to 100. Is that what was happening? Oh, interesting. It's because I left it running. Fascinating. Okay. Battery pull period. See to define the actions. Oh yeah, it asks for actions for both the charger, the fuel gauge, and the OLED. So there are the different actions there. Fuel gauge is there. OLED actions there. Okay, so there we go. Dump the OLED screen after scenario A. So what was scenario A? Pause, state ticks. All right, what is it? What's happening now? Resetting to a clean state. So we're going to call reset registers, power on reset. And then we're going to, okay, plug in adapter, fast charge 40. Okay, so let's see what it says. It still says 100%, 4.2 volts, and says full. Look at the way those L's are backwards. Is that actually backwards? Oh, the L's are backwards. How'd you do that? All the other letters look fine. What is it doing here? Okay, so it's going and getting the page 0, 2, 4, and 6. Oh, I see. Oh, interesting. I don't know what they consider pages. Those specific lines. So it looks like this. And then, I mean, there's like 66 different lines. So maybe there's 2, 4, 6. I don't know. Decode all 4. Oh, I see. Because we're rendering it like ASCII art kind of stuff. So it's actually going through and looking at the raw lines, which this is. There you go. So that's what it's saying. And that's what we're seeing over here. 100%, 4.2 volts. That's what we're rendering over here. So it's actually going SO, there's a slash 0, O/0, O/0, O/0. Okay. O/0. Interesting. So it's doing that. So and you can see in the display, like there's a line and then there's a blank and there's a line, then there's a blank, there's a line, then there's a blank, there's a line. So it's asking for 2, 4, 6, 0, 2, 4, and 6. So it asks for these bytes. And so not as they're rendered as in ASCII, but as they are actually, those are the bytes that are coming over. That's fascinating. Fascinating. Okay. Is that right? Check the current run state before redoing the scenario carefully. Wait, let me decode the programmatically rather than trying to hand avoid inscription errors. Oh, cool. So wrote a Python script in a scratch pad that goes and decodes the lines. And here are all the different glyphs. Well, that's super cool. How long would it take me to figure that out? 0 and O collide. Preferred digit looking context isn't handled, so just mark as ambiguous. Oh, I see. So it's got this 0 or O, and so they're like, yeah, that's fine. That's close enough. Okay, so then it reset. Okay, so what did it do? Step a small number of ticks. Check the OLED is right after the first pull. Reset and configure scenario A2 with a slower charge rate. Plugged in as adapter. Exchange set to 0. Charge state. Okay. Step through a full pull period and recheck the OLED for idle status. Set to not charging. Unplugged. Let's see what it's doing on this screen. Okay, 40% charging. Okay, OLED after unplugged. So what's this? What are the scenarios here? So we're going to go to unplug, then set not charging, and then step a bunch, and then check OLED.sh, which is going to be, you're so good at Bash. They're so good at Bash. Like, I spent a long time. I don't know if you know, I'm old guy now. Like, I spent a long time getting good at Bash, and they are so good at Bash, man. I tell you what, so good. I don't know why that L is backwards. Okay, it's finished. Stat now correctly reads idle. After unplugging, we test a discharging battery scenario and a fault injection. Okay, so it's going to set the mode to discharge and drain rate of 50, and then it's going to step a bunch and whatever, and it's going to check the number of ticks after doing that. Let me show you that GUI over here. So we've got 3 different numbers that are going up all the time. We've got the counter. This is actually the tick counter of the entire system. Okay, so this is not number of instructions executed. This is the tick counter of the system. Uh, because sometimes the processor sits idle. Sometimes, you know, and if we're talking about a unique time event, so we need a counter for the number of ticks that are going through. Okay. So that's that. The instruction counter, this is specifically to the Cortex M0. If we have another instruction counter on another processor, for example, that'll have its own instruction counter as well. And then here's PC, which is, you know, where it's executing in memory right now, where that's pulling the instructions from. And actually, we can even do that. Let's see. We've got this guy here, and we can actually do disassembly. Which when it pauses, you'll see it actually does the disassembly. It's a little processor intensive, so we don't do it while the system is running, just because we actually use, in order to show the disassembly, we use the same library. We actually have the processor do the disassembly for us in a, what do you call it, a stateless way. Now, I've seen other emulators that once you do the disassembler, it uses a different one. It's like it's doing the disassembly and running all the instructions, and then when you're like, oh, well, tell me, give me introspection, tell me about the instructions you're running. And I say, okay, well, here's the bytes. And then you have a different library that does a disassembly for me, which doesn't always match with the way that they're doing it in the emulator, because the emulator is taking shortcuts or doing weird things and whatever. So it's not actually faithfully executing the instructions like you would want it to. We don't do that. We are like, what you see is what you get, man. It's on the box. It's in the box. On the box, in the box. That's what you get with this emulator. So it's going down 23. You can see that it's idling. I don't, how do you even pronounce a backwards L? I'm really curious because that was the full scenario A, right? Yeah, it says backwards L on those too. That's crazy. Hold on, let me see what this did. See, it says forward L on these two. I'm really curious about this. Okay. Oh, it's down to 0. Still says idle. Virtual battery is 3.0. I mean, this is going to take a legitimate long time here. Oh, good. It figured it out. Did it pause? Doesn't pause yet, but it did. Battery correctly drained to 0%. Now let's test the fault injection. Yes, do it. Thermal shutdown fault. Nope. Oh, there's the word fault. I found a fault. How do I know when it's paused? Okay. Is that good? Fault. Forward L. Not backwards L. I'm really curious about this. Okay. Verify full state, then stop the session. Reset registers, plug in USB adapter. Set charge to done. Idle. SoC to 100. Did it list out the scenarios for me? I don't even know. It's giving them names A through E. All 5 scenarios confirmed the OLED tracks the simulated charger fuel gauge state correctly. Okay, adapter plugged, fast charge, 40%, unplugged, not charging, fuel gauge discharge mode, inject fault, thermal shutdown, charge done, SoC. One thing, look at that, it's not there. We're noting this. Emulator's charger model runs an autonomous shared battery charge simulation once you plug in power instead of charge state. My first attempt at a mid-charge snapshot overshot straight to 100% full because I checked after several wall clock seconds, which is a lot of simulator ticks. Reading immediately after configuring a small MCTL step, right after values are set, capture the intended immediate state instead. Everything reflects real firmware behavior. No emulator quirks or firmware bugs found. This run session stop containers up. You want to keep probing. Well, that's pretty cool. So that's it. We have an AI agent that validated the firmware that it wrote in a previous session by causing errors and other extraneous conditions in the attached I2C devices. Plugging, unplugging, it's just like, oh, here's normal behavior. Okay, so pretty cool. And there's more coming. We've got automated repeatable testing with an automated fault injection testing, so we can put these and we script those up. What about other manufacturers and different hardware and all that? Just slow your roll. We'll get there. Okay. Let's see what else. Oh, that's it. Oh, smash those like and subscribe buttons, and then head over to tuliptreetech.com to download your trial version of Emerson right now. We've got that STM32 F030 up there. You can go through the examples I've got. Join us in the Tulip Tree Tech Slack. We've got more stuff coming up, though. We've got more models. We've got more manufacturers in there, more I2C, all this, more. All right? So stay tuned, and we'll see what's happening next. And we can get you started building for your board without your board. See you next time.